Here we have a grid. We have points that both have at least one of the coordinate integers, and we know the Euclidean distance between them, which is d. The question is, what is the maximum possible distance when traveling by the grid lines between them? So there is two cases here. A is the segment between the points intersect both directions of the grid. So at least one vertical and at least one horizontal line. Then we can find first vertical line that intersects and the last vertical line that intersects it. And so we can travel like this. Which means the distance when traveling by lines between the two points is exactly the Manhattan distance between these two points. And as we have and also we know that so we have A plus B less equal to square root of 2 times B. Now this is achievable by just placing points like this. Hence, in this case, the maximum answer will be this. But there is another case when the segments do not intersect without losing generality. Let's say it doesn't intersect any horizontal line. So it looks like this. Here, this distance is the integer part of d. And say this AB, CD. So we to travel from here to here we need d minimum of and this A plus X plus B plus C is 2. This minimum is no more than 1. So we can achieve a total of integral part of t plus 1. And this number we can achieve only if d is less than this number. In this case, we need also to compare the previous achieved answers. But one can notice that if this is more, if this is more, then actually this answer will be better than this one. So we can compare them no matter what. Any questions about problem A? problem B. So these words are replaced with question marks. And so question marks can be replaced by any letter from A to Z, so that the words will be in lexicographical order. The question is how many ways to replace question marks there is. So we will, the total number of words is no more than 50. And slice of words no more than 20. Let us present a dynamic solution. Where first letter is a position inside word. Second index is letter. And then there is some starting word. And ending word. So suppose words from left word to right word have the same start, the same prefix of post length, and next letter is no less than letter. And this is all words in the dictionary that satisfy this condition. So we need to understand how we calculate this value. For the sake of simplicity, let's fill the word with some letter less than A minus 1. Let's call this letter, I don't know, omega, until they have the same length. So we pass the words with omega, so they have the same length. So now we need to write a function that would calculate this value. So if position is max possible position, then we had filled all the words in here. So if right word more right or left word, we will do if left word is right word equal to left word, we return 1. Otherwise, we have several similar words, and so this wouldn't be a correct dictionary. So otherwise, so if letter is more than Z, else returns 0. Now the first case, if there is no, here there is no word something is letter, exactly a letter. So we add add to result. This is fully letter. Now we need to iterate the number of words that actually have next letter equals to letter. So we iterate so if word E at position both is question mark and letter is omitted, then we break here. As we can replace question marks with omega, this fictional letter. If current character as not question mark and current character is not letter, we also break here. As current character should be we can put current character in here if it is not a question mark, it's not actually a current character. So otherwise, we will add to answer. Cos plus 1 as we fix it. Character 0 as we, not 0, but as we start from iterating letters again leftward. And I. And then if I less than right word, we will also multiply this by d of the same position, starting from letter plus 1, starting from I plus 1 to right plus 1. That's all the remaining words have some other letter in this position, and it is bigger. So we need to first calculate d of 0 and 0 and minus 1. We'll need to call our function. And from here on, we calculate our dynamic. So any questions about this one? All right. So problem C. Here we have a graph, full graph of m vertices. also have some A1 vertices, so that each edge between them colored in some first color. Then we have A2 vertices that have edges between them colored in second color, and so on. N is normally 5. And given values of A, we need to calculate minimum value of M. So the first observation is, for any two such such sets of vertices, they can intersect by more than one vertex. This is required and sufficient condition for the consistency of that each edge has only one color. So let's say that this set of vertices is 1, this is 2, this is 7. Then which means that this can be either 0 or 1. We have a total no more than 5 sets, which means we have no more than 10 pairs of sets. So, which means, okay, so what can be the minimum value? It is M is sum of AI minus number minus some number k. Well, suppose there is a total of t vertices that lies in more than one set. So let's say okay, so so the solution would be, we have we will do electroplating. So for we will process colors one by one. Okay, we will store for each vertex that we add to T, that we will add to T. We will basically store all colors, all previous colors, which it licensed in. So we would have some amount of vertices. Here, one. For each of them, we will know the colors from color 1 to color D, which you possess so far. Which is colored in. It should colored in no less than 2 colors. So when we process new color, we would then try to iterate through all these vertices and try to add the vertex of, say that this vertex is also vertex of color I plus 1. And at the same time we will look for consistency, so there should not be 2 pairs like this. And after that we may add some more vertices, no more than I. For like these, and so on. So, and also we only let pairs that are not already present. So we do such a backtracking. In the end, the M that will be achieved is sum I minus number of ones in the corresponding column, in the corresponding row, and plus the total number of vertices we use here. So as number of colors is quite small, this backtracking will run in time quite fast. So it's the solution of this problem. Any questions? Problem D. Here we have a puzzle like this one. And well, starting from some position here, the traveler goes down. Each time encounters intersection with some horizontal line, he'll take that horizontal line and then continue his journey. He will end in some position in here. The question is for each position at the top, we need to find where the traveler ends up in the bottom with the additional condition that some of these horizontal lines are actually removed. So, for example, in here, first traveler will end up here, second traveler will end up here, third traveler here, fourth traveler here, fifth traveler here. So first thing to notice is that no matter which horizontal lines we will remove, each two travelers will end up in different positions. How will we prove it? Suppose that they start journey at the same time at the top and going with constant speed down while crossing horizontal lines instantly. This way, in each moment of time, there would be no two travelers on the same vertical line. Because if one of them change his line, so does the ones that travel from this line. Now, suppose first thing to notice is how the travelers. Suppose all lines are present. Then each traveler goes several steps from position E. If E is odd, he goes to I+1, I+2, so on until he will go to position N. Then he goes to position -1 and -2 and so on. He goes to position 1 and so on. This is for odd. And for even, right? It will be almost same, just the other direction. So for each removed horizontal line, you can look at we can find out what travelers were supposed to interchange through that line. If all horizontal lines to the top of it were present. So we will have an array P, which is originally 1 to n. And let us sort removed horizontal lines from top to bottom. Then we will process them one by one. We will find which travelers, positions of the travelers in the original list that should meet here if all horizontal lines up from here is present. And then all we need is just exchange these two positions in this array. Because the fact they won't actually exchange positions here. It is the same as we just exchange their position in the original array. So we do this. After this, we need for each traveler to find if he starts in his position and all horizontal lines are present, in which position he will end up. And so the answer, so let's say the traveler even would end up in position QI. So the answer of QI will be QI. Any questions? Okay. Skip problem E. Just a moment. So problem G. So here we have some kind of intersecting polyline. And we want to know whether it can go to a point in a line. So, first thing to note is that we basically need to understand whether we can push each segment of a line through this polyline. Each segment of this polyline through this line. So let's look at some segment. We have some kind of polyline here. And what we need to know for each point of this line, we have polyline like this. And so we have like this angle, and there is some maximum value of this angle at which this part of polyline won't cross the line, and some minimal amount. So alpha is between 0 and 1. But we also have some conditions on the top part of the polyline. There is some and hence for each part for line to go through, for each point it should be true that maximum is more than minimum of maximum. This angle, let's just calculate now the minimum angle of the 1/2. How will we do this? This angle is based on some point here, which has the minimum possible angle to the axis. So let's note at this point, it may be not the same point for each point of the segment, but we can divide the segment into subsegments. So in each subsegment, this will be the same point. After we do this, this angle will be, let's call this angle beta. symbol delta will be function on this segment, say from 0 to some value t. So let's say when this is 0, this point is has this coordinates. So this basically let's also rotate for the time being. So the segment is perpendicular to the axis. So it will be x, I will minus also function minus this is from 0 to L, and the point is coordinate t. So we also have some point here. So this one angle is beta, and basically we can have minimum angle as half of the t minus beta. This is so we have also some angle here for the same segment, which is so alpha 0. The same way we can calculate, so let's say this is 0. We can calculate the same way for other angles. Or rather this. And so we can these two functions will meet somewhere. So this angle goes like this. So we can once again divide the segments into two parts where only exact one of these angles is the minimum. We can divide the same, we can say the same thing about maximum angles. And then we have two functions, is tan, what's the tan? The difference of such functions will be convex. So we can find the minimum, not convex, but like this. So we can find the minimum value using internal research and check whether in this minimum value this condition will hold. So basically we need to do a lot of trigonometry. The limit on the number of segments is 1000. And here we have a single subsegment for each vertex of the polyline. So the total number of segments here will be else like this. So we have a total of n squared segments on the whole of polyline normal than this, but actually quite much, or quite smaller amount. And well, so then we will also tell the research. So this is our solution. Questions? Okay, let's have a 10-minute break then. Problem H. We have a graph which is a tree. Vertices are numbered. And the property of this tree is that it's a rooted tree where index of which parent is less than the index of the vertex. So we want to, for each k, we want to find well, the first thing we need to notice that despite here there is no more than n, we can replace it with k because well, suppose there is some sub-tree and suppose the minimal vertex with the minimal distance is somewhere outside the sub-tree. But if we go in the direction of sub-tree, so if we go up, obviously the total distance will go down by the weight of the stage times k. So the vertex where this minimum is achieved is always inside the it's always between the vertices of sub-tree. So we can go and vertices one by one. Suppose we have some answer for the previous some previous sub-tree, and now we have new vertex. So how the answer can change? Obviously, the only way the answer can change is it can shift through some edges on the path from the current answer to the emulated vertex. Now, suppose we know the current minimal sum, which is S. So the distance between this vertex and all vertex is S. First, we need to add the distance to the new added vertex. We can do so, but first find an LCA. In this vertex, in this vertex. So in this case, it's the root of 3. That case stands for lowest common ancestor. And next, we need to find, we can, for each vertex in the original tree, we can find the sum of distance, the distance from the root. So, the total path from this vertex, say vertex I to newly vertex J, is distance from the root to Y plus distance from the root to J minus 2 distances from the root to the CA. Also, we can store ordering of vertices in LCA order, not the DFS order. So for each vertex, we will know its order in DFS order. What is DFS order? Let's start from the first vertex, add it to the DFS order, and then subsequently add the first order of subtrees that have roots with children. So the first order of order 3 is 3. So this way, if you have a segment tree, which for a given segment will return number of vertices we already added, we already processed in this graph. So query. So we can find the number of vertices already processed in any subtree, in any root of subtree, by finding, but squaring it from the DFS order of the root of such subtree to the DFS order of the last vertex of the subtree. So this way we know. Now what we need to do, we need to shift several times on the path from the last answer to the newly added vertex. So when we shift, how the distance changes. For each vertex in subtrees in this subtree, so suppose this weight is W. For each vertex in this subtree, we will add W to the answer, and for each vertex of remaining, we will subtract W from the answers. So if number of W is added is less than the number of W subtracted, the answer will go down. Otherwise, the current vertex is actually the one that is where this minimum is achieved. So let us prove that on each step of our algorithm we will shift no more than one time. So as this vertex was the best last time, the difference between this, if now the number of vertices in this part of 3 more than number of vertices of this part of 3, then previously it was equal. And so when we add this vertex to this part of 3, now there is more vertices in this part of 3 than in this part of 3. So it wouldn't be beneficial to us to go any further down. And so, as on each step we will travel no more than one time, all our queries goes to this, to LCA and to our segment tree. We will work in algorithm time, so total working time will be like this, which is more than sufficient to succeed. So, based on this problem, let us talk about algorithm of finding the least common ancestor. So, suppose we have a rooted tree. And we want to quickly, for any of the vertices in this tree, quickly answer what is the least common ancestor. So there are several ways to do this. The easiest one that you will need most of the time will work in logarithm time for each query. We will have preprocessing of n log n, and we will have memory. So for each vertex in the tree, we will store following values. First, we will store level, such vertex, namely the distance in the end distance from this vertex to the root. And then for each e between 0 and binary logarithm of n, we will store which vertex, we will store which vertex v, which of the path from I to root, and a is the distance between v and I. So we say is 2 to the power of j. Or otherwise, if distance between root and I is less than 2 to the power of j, then Vj is actually root. This way, for any vertex in logarithm type, we can find the vertex which is exactly L levels higher than current vertex and is ancestor. How we can do this? We will, for each, we will go from j from 0 to n. So suppose the starting vertex is V. So if L and 2 to the power of j, so if L has the power 2 to the power of j in its binary representation, we will just say that V is, we advance V to its ancestor that has a distance to the power of V. So, now, how do we find the RCA? Let's look at our vertices. Say vertex I and vertex j. Say level of j is more than level of I. Then we first advance vertex j so that are on the same level. And then we can have a binary search on the not exactly the binary search. So let us first try to advance these vertices both by the maximum value. If they are the same, then we will advance them lower and lower until we find the index j such that this case, such a with k is equal to j with k, while a with k minus 1 is not equal to j with k minus 1. Then we will both say that a advance them by 2 to the power of k minus 1 levels, and continue from here with level k minus 2 and so on. So this way it took logarithm time to make this the same level, and then logarithm time to find the actual LCA. This is one of the ways. This is the easiest basically way to do this. You can also have another algorithm which has the same complexity for the querying, but reprocessing would be only this, and memory will be also this. This can be done if you build segment tree on DFS order. Not exactly on DFS order. We will use the following order. So, say, let's call it in order. which is not exactly inverted but still, because we have non-binary tree, which is for vertex V, it is V in order of V1, V in order of V2, V, and so on. In order to VK, V. Where V1, V2, Vk is the children of V. So let's build then the segment 3 on this order, which will return the minimum, the vertex with the minimum level between the vertex of requested. So query is index of vertex with minimal level. That way to find the LCA, we just need the query this segment 3 from from let's say that the first time the vertex V is in order array. Let's say that it's P of V. So LCFA J is query on minimal Pi Pj to maximum of Pi Pj. So this is two algorithms. So there is also, this algorithm is a little bit harder to write, but if you are constrained with memory, you probably can do this. There is also an algorithm that works in this kind of single query, but we will not discuss it here because it's quite harder to implement. And at the same time, the benefit is too small. It's very rare occasion that this will help you fit into 10 minutes. Let's move on. Let's discuss problem J. By the way, you can find this implementation in the same library as string algorithms I sent you after the first day. There is quite a few algorithms in the library. I hope they are all correctly implemented. So, problem J. Here we have some parallelepipeds in n-dimensional space. So L1. So and we want to find part of it, which is also part of some simplex. In the same line, we play same dimension, the same space, namely, such that the sum is no more than, if I recall correctly, S. So let's look at, for simplicity, two-dimensional case. So let's use inclusion-exclusion principle here. So let's look at this vertex. The part of the triangle which starts at this vertex is this. Let's add it to the answer. So each part should not be in the answer. This one and this one. Basically, the same, the triangles based on this and this vertex. But suppose now that the rectangle lies wholly inside our triangle. Then we had excluded this part 2 times. Which means we need to add square of the triangle that is based on this vertex. Now, let's also notice that the square of this triangle is only dependent on the sum of coordinates, only dependent on x plus y in this case. As there is too many dimensions in our space, we can just try to add and subtract volume for each vertex of our parallelepiped, because it will have such time and no more than 300, if I recall correctly. Yes. It is too big. So let us, for each, basically, for each vertex, we will need to find the sum of its coordinates, and the coordinates will be either 0 or a, e. And also you will need to add the corresponding volume if we use even number of 0 coordinates. No, not even number of 0 coordinates, even number of non-zero coordinates. And we need to add 1 to the structure if we use odd number of non-zero coordinates. So we basically, as the actual volume only depends on the sum, we can use Knapsack approach to this. So let's start with some array D, and D0 is equal to 1. Then let's, for each side, proceed as follows. Let's relax each value such that for E starting from sigma of L process so far, to 0. We say that D of I plus LK, we subtract the value of DI. So as we add one additional non-zero coordinate, the sign will always flip. So we need to subtract the value. So we go through this. We have some values DI. Let's also know that the volume of such simplex, is actually s to the power of n divided by n factorial. As we need to find the answer times n factorial, so for us this way of working is just s to the power of n. So what we need to do then, we need to calculate sum from e to s minus e to the power of n. Here. So as we have some time left still. Oh, any questions about this particular problem? Okay, we have still some time. Let's talk some about that matrix and how it will help us with finding matching is non-bipartite graph. So, many of you probably heard about the problem of finding matching in bipartite graph. Which is to find the maximum number of edges such that the ends are all unique. Well, this problem can also be solved to in the general graph through with a bit more complexity. So there is an Eight's algorithm. As you may see, there is many algorithms that all have one algorithm that works in cubic time. And well, particularly, no one provided during the contest because it's rather hard. So we will talk about algorithm based on that matrix. Which would give us the size of the perfect matching at the same time, and then this time the matching, the actual matching itself. For this, we need to first construct a type matrix. What is type matrix? It has 0 on the main diagonal. Here is the main diagonal. And then it has some values in other places. This matrix is antisymmetric, so the values in here are always negate of the corresponding values over the diagonal. So xij is equal to some variable, independent variable, if there is edge if there is edge between I and j, and is 0 otherwise. So this is called type matrix. And what interesting about this matrix, let's call it T, is that there is perfect matching. And perfect matching is matching of the size that use every vertex. There is perfect matching if and only if its determinant is non-zero. And by non-zero, I mean that there is such you can assign values to each independent variable in such a way that the determinant will be non-zero. There exists such a way. How will it actually help us? Because of course we can't calculate the polynomial that will be the determinant of this matrix. It has too much variables, such amount of variables, and so even more combinations of these variables. Well, we actually can replace each independent variable with some random variable. Suppose we replace them with some random values from 0 to b, and then we calculate the determinant of this matrix modulo p. That way, the probability that graph will have perfect matching while we will achieve result 0 is exactly this. So we can take a couple of sufficiently large values of p and then try 2 or 3 times, and if each time we will yield results 0, then there is this very big probability, no perfect matching. But suppose we need to find the size of the maximal matching. Well, this is exactly rank t divided by 2. You can find rank using Gauss elimination, just as you can find determinant. And hence, we can find the size of maximum matching in this time. Now, suppose we need to find the matching itself. There is another result called the lowest theorem. Which says, suppose we have the perfect matching, so the amount of that matrix is non-zero. Then we can find the reverse matrix for that matrix. Then the probability that, suppose there is some element, say, that is not equal to 0 in this matrix. Then with big enough probability, there is a perfect matching. matching that contains the edge IG. So our whole algorithm will be like this. First, we need to find the rank of that matrix. At the same time as we finding the rank, we can actually find the vertices that will be in the perfect match, exactly the ones where which remains with ones after we complete our Gauss eliminations. Remains non-zero after we complete our Gauss elimination. After this, we will, using Gauss elimination again, revert to the touch matrix, find any non-zero edge in the non-zero value in it. This is part of perfect matching. Now we can remove these two vertices from the graph. We have new touch matrix, and we can find the revert matrix again. So we do this edge by edge. So as we have total of n edges, and each reversal will work in fourth and cube time, the total complexity of algorithm will be like this. So any questions about the top theorem, lowest theorem, and corresponding algorithms? Okay, if there's no questions, you can now come ask questions you don't want to ask publicly. The link for today's contest will be sent out as soon as I find some working internet. So today's contest will be the World Championship of 2013. I hope you have not yet solved this contest. It's a very interesting contest. So good luck at today's contest. That's all.